Hi, everybody. So now I want to do a few more, maybe a little bit more complicated examples of factor groups so that we have a nice library of examples to turn to when we try to figure out what's going on. So the first example I want to talk about is the case where the group G is the 2x2 invertible matrices with real entries, and the group H is the subgroup of that group consisting of matrices of determinant 1. And these are groups that we've looked at before. And the first thing to observe, and I think we've observed it before, but it's good to check, is that SL2R is a normal subgroup in GL2R. That's important because if we're going to make a factor group G mod H, we have to start with a normal subgroup, not just any subgroup. And to check that, we need to know that if G is any element in GL2R, we need to know that when you conjugate, you get H back. And so what is that saying? That's saying that if H is an element in SL2R, so it's a matrix of determinant 1, and I take any G in GL2R, and I look at GHG inverse, I want to know, is this in H? And for that, I can just check that the determinant of GHG inverse is the determinant of G times the determinant of H times the determinant of G inverse, since the determinant is multiplicative. And since these are just real numbers, we can cancel the ones that we can't do it with matrices, but we can do it with real numbers, which is what determinant of G is. And so we're left with determinant of H, which is equal to 1. So if you take a matrix of determinant 1 and you do GHG inverse to it, it's still of determinant 1. And therefore, SL2R is a normal subgroup. Next, we need to know what the cosets are. And again, this was a homework problem, so I'm just going to briefly remind you what the answer is. If we take a coset, a left coset, and we look at the set GH, and if X is any element in that coset, then the determinant of X is equal to the determinant of G. Every element of the coset GH has the same determinant as G. And conversely, suppose you have X in G and its determinant is equal to the determinant of G. Well, then if we look at X times, let's do it this way, X inverse G, then this tells us that that X inverse G here is equal to 1, and so we have that that it's in SL2R. So the coset XH is equal to the coset X times X inverse GH, which is equal to the coset GH. So basically, what the cosets do is they divide GL2R up according to the determinant of the matrices. So what we say, in other words, is that the two cosets AH and BH are the same if and only if their representatives have the same determinant. And maybe more explicitly, if we let M be an element in R star, then the matrix M, if we look at the coset given by M, every coset is of this form. because this matrix has determinant m. And so this is the set of matrices G in GL2R, where the determinant of G equals m. So every coset basically corresponds to a possible determinant. And now finally we're in a position to prove the proposition. We need to give an isomorphism from R star to G mod H. So that means it has to be a bijective map and it has to respect the multiplication. And the map that we're going to take is you take an m, which is a real number which is not 0, and you need to make a coset, and the coset you make is the one we just described up above. And we need to prove that this is an isomorphism. And for that, we need to check, first of all, that it's bijective. So we need to check that it's injective. In other words, we need to know that if f of m1 equals f of m2, then that means that the coset m1001h equals the coset m2001h. And that happens only if the determinant of m1001 equals the determinant of m2001 by the calculation that we did earlier about the coset representatives. In other words, that means that m1 has to equal m2. So f is injective. Next, we need to know that it's surjective. And for that, we take any coset GH and we let m be the determinant of G. And then f of m is the coset m001h. And I claim that's equal to the coset GH. And again, we more or less did that before, but we can check that out just by seeing because m001 inverse times G, the determinant of that, is 1, because this has determinant m and this has determinant m, and so m inverse times m is 1. And therefore, f of m, f is surjective. And finally, we need to check that f of m1 times f of m2 is f of m1, m2. And for that, we use the fact that f of m1, by definition above, is the coset m1h, and f of m2 is the coset m2h. And using the group law in the quotient group, f of m1 times f of m2 is m1h times m2h, which is m1 m2h, which is equal to f of m1 m2 by definition. So we've shown, therefore, that if you take the group GL2R and you mod out by the action of SL2R, you get a copy of R star. In some sense, what you've done is you've pulled out the determinant by taking this quotient group. Okay, next example. Let's look at the case where G is the dihedral group with 2n elements, but let's assume that n is even. So this is like the symmetries of the square or the hexagon or the octagon, where the number of sides in our polygon is even. And let's let H be the center of G. And we've worked this out before. In this case, H is a 2-element group. It's generated by E and the rotation halfway around. Remember, maybe it's worth remembering that Dn consists of 1 r, r squared, r to the n minus 1, s, sr, sr squared, sr to the n minus 1. where r to the n is the identity, s squared is the identity, and SRS is R inverse. And from that, you can calculate anything you want to know about the dihedral group. And we've figured out what the center is. And we already showed, and I won't rehash it, that the center is automatically a normal subgroup. So H is normal in Dn. And the cosets, there are, so Dn has 2n elements. So the quotient group Dn mod H has n elements. And what are the cosets? Well, the cosets are, again, you have H, RH, R squared H, and so forth. But when you get to R to the n over 2 minus 1H, the next one, which would be R to the n over 2H, is H again. Because R to the n over 2 times E R to the n over 2 is R to the n over 2E, which is H again. So you have a collection of cosets corresponding to R, and then you similarly have a collection of cosets corresponding to the SRs. And this gives the right number of cosets. It gives n over 2 times 2, which is n cosets. And because these sets are all different, they account for all of the cosets. And I think we've looked at this before also. So the real question is, what's the group law? And the key thing to notice is that that R, H, acts like the R in a dihedral group of half as many sides, because it acts like if, RH, then you have RH squared, which is R squared H, RH cubed, which is R cubed H, all the way out to R to the RH to the n over 2 minus 1, which is R to the n over 2 minus 1H. And then finally, if you had RH to the n over 2, you would get R to the n over 2H, but R to the n over 2 is in H, so that's equal to H. So R has order, RH has order n over 2. And SH squared is S squared H, which is H. So SH has order 2. Just like in Dn. And what about this relation? If we look at SH, RH, SH, then by the group calculation in the quotient group, that's SRSH, and that's R inverse H, just like before. So this looks exactly like a dihedral group. And to see, in fact, the isomorphism from Dn over 2 to Dn mod its center, it's probably easier to write it in the other direction, is let's call these things, instead of R and S to keep them straight, we'll call them, we have 1 sigma squared out to sigma to the n over 2 minus 1, and then we have tau sigma out to tau sigma to the n over 2 minus 1, where tau squared is the identity, and sigma to the n over 2 is the identity, and tau sigma tau is sigma inverse. And we send sigma to the I goes to R to the I H, and tau sigma to the I goes to SR to the I H. And both of these formulas are satisfied. And this map is bijective. I mean, we've listed all of the 2n elements of Dn over 2 and all of the 2n cosets of Dn mod Z. And so we have this nice example that if you take the quotient of the dihedral group by its center, if n is even, you get the dihedral group for half as many. So D6 mod its center is D3. Let's look at one more example, and that has to do with the quaternion group. So the quaternion group has 8 elements, plus or minus 1, plus or minus I, plus or minus j, and plus or minus k. And it has this normal subgroup H, which consists of just minus 1 and 1. In fact, this is the center of the quaternion group. So the cosets correspond to, well, in some sense, H, and then there's the coset that consists of I and minus I, and the coset that consists of j and minus j, and the coset that consists of k and minus k. So the cosets are like plus or minus I, plus or minus j, and plus or minus k together. And this is a group of order 4, and we already know that all groups of order 4 are abelian, and there's really only 2 possibilities. And here we can just compute to see what we get. So this is IH, this is JH, and this is KH. And we have that IH squared is minus IH, which is H, because minus I is in H. We have JH squared is minus JH is H, since minus J is in, sorry, this is minus 1, not minus I. This is minus 1. Since minus 1 is in H, minus 1 is in H. And finally, KH squared is minus 1H, which is H, since minus 1 is in H. So all 3 of these things, when you square them, you get the identity. And then when you multiply them, like if you multiply IH times JH, you get KH. But if you multiply JH times IH, you get minus KH, but that's KH again, because minus 1 is in H. So it's like you've taken the quaternions, where the multiplication, the order does make a difference, and you've said, I'm just going to call x and minus x the same. And if you do that, then the group magically becomes commutative. And in fact, the group that you get is Z mod 2 cross Z mod 2, where you can think of, let's say, IH goes to 1, 0, JH goes to 0, 1, and then IJH, which is KH, goes to 1, 1. And this will be, and then of course H goes to the identity, and that will be an isomorphism between this group with 4 elements and the group Z2 cross Z2.